So good afternoon students. Now we will continue our internal voltage control technique part. So in the internal control technique we will study about single PWM in the next lecture. Now we will see the multiple PWM techniques. So in this technique two signals are there. One is the carrier signal and the second one is the reference signal. So carrier signal is triangular in nature and having a time period of Tc, frequency equals to Fc, and having amplitude of Vc on the y-axis, and a reference signal having amplitude of Vr, or we can say that as it is a AR, or the time period there is a Tr and the frequency is Fr. So this is the two waveforms and which are compared in the comparator, and if two signals there is a Vr and Vc are passes through the comparator, then it will compare that either a carrier signal amplitude is higher or a reference signal amplitude is higher. So if the Vc greater than Vr, then turn on T1 T2 of the full bridge inverter thyrstors T1 and T2 and output voltage which is equals to VDC. So VDC, or we can say that it is a Vs, that is a input voltage. And if minus Vc is greater than Vr, there is a minus Vc in the negative half cycle and this is minus Vr. So if minus Vc is greater than minus Vr, or simply we can see that is a Vc less than Vr, then T3 T4 are turned on and output voltage which is equals to minus VDC according to full bridge configuration when thyristor T3 and T4 are on. So what is the output waveform when these pulses are generated? By comparing the amplitude of the reference and triangular pulses, then output voltage, this is the output voltage waveform, that is a V naught, and so the this is the intersecting point of it is compared at 3 points. First one is the triangular pulse, second one is the triangular pulse, and third one is the triangular pulse, and this is the reference pulse. It intersect at 3 points. So if we draw perpendicular lines, then we will see that the pulse are generated. So three comparisons are made there, and in these all the three comparisons, Vc greater than Vr. So Vc greater than Vr, then V naught equals to VDC according to switching logic. So three pulses are generated. So these are the three pulses and having amplitude of VDC in the output voltage waveform. After pi, Vc less than Vr, so output voltage pulse having amplitude of minus VDC is generated in the negative half cycle, and three comparisons are made there because three intersecting points are there. So three pulses are generated in the negative half cycle from pi to 2 pi. So it is called the multiple pulse, because multiple PWM, because more than one pulse is obtained in the each half cycle. So if we see TR, this is a TR is the reference, it's the time period of the reference signal. So up to 2 pi it is a TR of the time period of the reference signal, and the reference signal in this diagram is this is rectangular in the shape. So it is a rectangular shape having a time period of TR or it is a 2 pi. So if we divide is it TR by 2 and TR by 2 up to pi, so it's a TR by 2. So now number of pulse, assume let that n pulses are generated in the each half cycle, although three pulses are generated here, but if we general case we will take, then number of pulse equals to n, then this 2d, which is the pulse width in each half cycle, as we can see in earlier lecture, that is 2d is the pulse width in each half cycle of pi 2d. So if we divide by n, then pulse width of individual pulse is obtained. So total pulse width in each half cycle is 2d, and each pulse it is a 2d by n, because this 2d is total pulse width of 2d is divided into 2d by n, 2d by n, and 2d by n respectively. And this is the time period of and three oscillations or three cycles are completed by this carrier waveform. At the same time, only half cycle is completed by this this reference signal. So we can make both are equal, then we will see that. So from 0 to pi, 3 Tc, that is a 3 into time period of carrier waveform. So three cycles are completed by this triangular waveform up to pi. So it is a one cycle is there, the second cycle, this is a third cycle. So 3 Tc equals to Tr by 2. So if we made equal to 3 Tc equals to Tr by 2, and this is if we put Tc equals to 1 by Fc, that is a frequency inverse. So Tc equal to 1 by Fc, and this Tr equals to 1 upon Fr. Then we calculate the ratio of Fc upon 2 Fr. So Fc upon 2 Fr obtained to be 3. So 3 means according to our output voltage waveform, 3 are the number of pulses. So this ratio we will recognize that Fc upon 2Fr equals to number of pulses generated in each half cycle. So Fc upon 2Fr equals to n general, because we will assume number of pulses equals to n. So n equals to 3 here. So n equals to Fc upon 2Fr. So by this formula we can calculate the number of pulses generated in each half cycle. Fc is the carrier frequency, Fr is the reference signal frequency. Now we're interested in finding the width of this generated pulse. So we will take this portion of the waveform, above waveform. So this waveform, this is the carrier waveform, which is triangular in nature, and this is the reference waveform. So we will cut this part here and we will zoom the view of this waveform. These parts are shown in the below figure. So this is the triangular waveform and this is a reference waveform. So it's marked as A, B, C. It is a triangular, and this is a reference signal DE. And this O point is the midpoint of this reference line, and this M point is the midpoint of this line BC. So if we apply a similar triangle concept, then triangle ADE. So triangle ADE is ADE. This is small triangle ADE, and this is the ABC. So this ABC is the full triangle, big triangle is there. So this whole AM equals to VC. Why VC? Because it is the amplitude of the carrier signal. So whole amplitude up to AM is VC, and this OM is equals to VR, because it is a reference signal amplitude up to VR. So if we subtract this VC minus VR, then we will obtain AO, which is VC minus VR. And this pulse is generated up at the comparison of these 2 points. So if you draw perpendicular line from D and E, then pulse is generated having width of W. Say W is the width of the pulse generated, and this pi by n. How we can obtain this pi by n? Because half cycle time period is pi. So if 3 pulses are obtained, then we will divide pi by 3, pi by 3, pi by 60, 60, 60. That is 180 degree. So in general, this is a 1 pulse. So pi by n will be there. So now we'll apply similar triangle concept according to this OA. That is this is small height, and this AM, that is a whole height, which is equals to DE, that is a small horizontal part, and this is a vertical. This is a horizontal part BC. Whole vertical. This is a horizontal part BC. So AO upon AM barabar or equal to DE upon BC. So if we make these sides equal, then and put the values, OA equals to BC minus VR, AM equals to BC, and this DE equals to, we assume DE will be width of the pulse, this is W here, and this BC equals to pi by n. So if we calculate W from here, then it will be equal to pi by n 1 minus VR upon VC. So here the term comes VR upon VC. What is the meaning of this VR upon VC? It is defined as the M, that is a modulation index. So if we change the VR, that is the amplitude of the reference signal, we can change the modulation of the waveform, that is a amplitude. So this VR upon VC is called modulation index. So pulse width calculated to be pi by n 1 minus VR upon VC. So in first case we will calculate the number of pulses, that is Fc upon 2Fr, and this second expression, that is a width of the pulse is calculated. So one numerical is there. We will solve this numerical to assume this whole concept. A triangular wave having peak amplitude of 100 volt, that is VC is given, that is 100 volt, and frequency 400, that is Fc equals to 400 Hz, is compared with the AC square wave having peak value 70 volt. 70 volt, what is 70 volt? That is a VR, and frequency, it is a FR, because reference signal is there. So both are compared such that it will give pulse when instantaneous value of triangular wave is greater than the square waveform for the positive half cycle. So in positive half cycle, we will know that AC will be greater than AR, or VC will be greater than VR. So pulse is generated in the half cycle. So find the number of pulses generated in the positive half cycle. So it will ask that find the number of pulses generated in the positive half cycle up to pi, and also find the width of the each pulse. So we will apply the formula n equals to Fc upon 2Fr, put the values of Fc and Fr. If we will calculate, the number of pulse obtained will be 4, and W, which is the width of the pulse, so it is W by it is given by pi by n 1 minus VR upon VC. If we put pi equals to 180, n will be calculated from the above, which is 4, and this is 1 minus VR upon VC. VR is given that is 70 volt and VC should be 100. So from this we will calculate the 13.5, which is the width of the pulse. So in this way we will complete the multiple pulse width technique. So why will need to study this multiple pulse width technique? So it has the advantage that it will reduce the lower order harmonics but increase the higher order harmonics. So increasing the higher order harmonics is advantage because increasing the higher order harmonic, that is a number, so that higher order harmonics can be easily filtered out, but lower order harmonics cannot be easily filtered out. So this technique has the advantage of that it will remove the higher order harmonics, so or increasing the higher order harmonics so that they can be easily filtered out. And but one disadvantage there for this technique, that output pulse having a peak amplitude is decreasing as compared to single PWM. So if you calculate from the Fourier series analysis, then the output RMS voltage obtained by this multiple PWM, then it will be lower, because if we calculate the peak value of the fundamental component from PWM expression for the multiple PWM case, then it will be a lower amplitude as compared to single PWM case. So some of the disadvantages are there and some of the advantages are there in this technique. So because the peak amplitude is decreasing by this PWM technique, we will improve this disadvantage by employing the sinusoidal pulse width modulation technique. So in the next lecture we will see sinusoidal PWM technique, by which we can analyze the Fourier series part, as well as we can see the how the peak amplitude is now improved in magnitude. So thank you.